So in this video, we're going to go over homework 6. Start with problem 1. So in the very first part, I'll do this one from the beginning. Others I've already put on the screen. F is the parabola. 7 times x squared minus x minus 4. And just to see what's going on, if we plot f of x, this is the nice parabola. Let's just look at this a little bit more closely. It's interesting. Yeah. So here is the vertex. It's not clear exactly where it is, but we will find out. So where is the curve increasing? It's increasing where the derivative is positive. So the derivative of the function at x is this. And if we write the inequality solve, the derivative greater than 0. For what x is the derivative greater than 0? From 1 over 14 to infinity. So we could make the comment f of x increasing on this interval above. That's where the derivative is positive. Where is the derivative negative? Minus infinity to 114. So the function is decreasing on this interval. Well, of course, it's clear where the function is going to be 0. Where is the derivative equal to 0? At 114, 1 over 14. So x equals 1 over oops, hard to write like this. Let me just write. This is the, well, in fact, we know if it's decreasing, increasing, this is the relative minimum. And in fact, oops, I have to comment that by putting this, there we are. If we want to double check, the second derivative of the function is just 14. So if we were to evaluate the second derivative at 1 over 14, of course, we would get 14. So the critical point, right? Critical point, I'll just call it CP. That's the point where the derivative is 0. Is a relative minimum by the second derivative test. Also, the second derivative is positive everywhere. So second derivative always positive means the function, the graph, the curve is concave up everywhere. So in particular, no inflection points. Because the second derivative never changes from positive to negative. So that's everything we had to do. Problem 1b, we have a cubic curve. Here it is. You plot it, looks like this. Up to 4. And maybe even just go up to 3 to, oh yeah, very nice. That's the cubic curve. Where is it increasing? Where the derivative is positive. So if you can't use f solve within an inequality. So you solve and you get this explicit form. I'd rather see it as decimal. So I solve the inequality and then I evaluate f. That means convert to decimals. I get these two intervals. So in these two intervals, the derivative is positive. The function is increasing. Here's the first interval up to about minus 2.4. Here's the second interval from about 0.069. Similarly, here is where the derivative is negative. So in this interval, you can see it on the graph, the function is decreasing. Where are the critical points? At these two numbers. These are the two critical points. Minus 2.4, that's this relative maximum, plus 0.69, that's the relative minimum. If we look at the second derivative, here it is. It's negative in this interval, so the curve is concave down in this interval. Here it is, concave down. Whereas the second derivative, oops, let's see. Here's where the second derivative is negative, whereas the second derivative positive on this interval. Here. So here the curve is concave down, here is concave up, and at this point where the second derivative is 0, there's an inflection point. So inflection point at x equal minus 1.1666 and so forth. That's problem 1b. Maybe just so I have them all here, I'll put in problem 1c. So problem 1c, we have the function x goes to minus 2 times x divided by square root, that's the maple command, of x squared plus 1. Minus 2x over the square root of x squared plus 1. If we plot f of x, what does it look like? Uh-huh. Yeah, something like that. It's kind of interesting. It's negative when x is negative. It's positive when x is positive. It's 0 is 0. So what is the derivative of the function? That's what it is. Let's see if Maple will simplify it. Oh, this is much simpler. Now, actually, you can tell just by looking, this denominator is always positive. So this is negative. So this function is always decreasing. So if we said solve the inequality d of f of x less than 0 for x, this just means all x. If we said solve the inequality derivative of x greater than 0 for all x, you get nothing. So f of x is decreasing for all x. Strictly decreasing. Derivative's never 0. What about the second derivative? Let's see what that looks like. D at 2 of f of x. Let's see if we can simplify that a little bit. So again, you look at the second derivative, x squared plus 1 is always positive. So this function will be positive when x is positive, negative when x is negative. If we just want to double check that, let's say solve the inequality, second derivative greater than 0. 0 to infinity. So this function has the second derivative positive from 0 to infinity. That means it's concave up from 0 to infinity. It's decreasing, but it's concave up. Where is the second derivative negative? Minus infinity to 0. And again, we know what the answer is going to be. When is the second derivative equal to 0? At 0. So x equal 0 is an inflection point. So this function, it is concave down till it gets to 0. There's an inflection point. Now it's concave up, but everywhere the function is decreasing. It has no relative minimum or maximum. And you can actually see what's happening as x gets bigger and bigger. If this is the function, as x goes to infinity, this denominator is like x. It's the square root of x squared, roughly. This is going to be approaching minus 2. Let's just see whether Maple can calculate that for us. What is the limit of the function f of x as x goes to infinity? Okay. That's what we want to find. With the limit command, when you use a capital L, it just writes it out in standard mathematical format. If you want the answer, you have to write this with a lowercase l. So equals minus 2. As you go to infinity, this is approaching minus 2. And what happens as you go to minus infinity? Minus sign there goes to plus 2. So on this graph, if in addition to plotting the function f of x, I also plot the constant function y equals 2 and y equals minus 2, so I'm putting in these horizontal lines, you see how, as x goes to infinity, this graph is approaching -2. As you go to minus infinity, the graph is approaching plus 2. So you can see very nicely what is going on. Okay. 1D, this is the function. The graph looks like that. Kind of interesting. You can actually see that as x goes to infinity, x over x plus 3 is approaching 1, so this is approaching 0. So this graph is really approaching asymptotically to just the line x over 2. And if I plot that along with the function, oops, why didn't it do this? There we are, yeah. So this red line is the line y equals x over 2. In fact, if I increase this range a little bit, maybe x going from minus 20 to 20. Yeah, you see the blue is the curve, and it's approaching y equals x over 2 as you go to infinity. It's not defined where this is negative, which is from here to here. In any case, the blue is the graph of the function. This is the derivative. If you graph the derivative, it's interesting. You can see the function is, the derivative is positive here, and here it's negative, which means here the function is increasing, here it's increasing, and here it's not defined. So this function where it's defined is always increasing. The derivative is positive everywhere. Let's just go back and do one other thing just out of interest. Suppose I wanted to solve, you see, the logarithm's only defined for positive numbers. So when is x over x plus 3 less than 0? Solve that for x. From minus 3 to 0. So from minus 3 to 0, this is not defined. That's why on the graph, let me just take out the x over 2, which is, see here, from minus 3 to 0, there's no curve. It's just not defined there. On the closed interval. When x is 0, this is 0, not defined. When x is minus 3, this is undefined because the denominator is negative. So here's where the function is increasing everywhere. Right? This is the function. It's always increasing. No relative minimum or maximum. Second derivative is positive. Minus infinity to minus 3. So here curve is concave up. Here you can see it's concave down. And when you ask where is the second derivative negative, it's 0 to infinity. Okay. In problem 1e, this is the function. The graph looks like this. Here's the derivative. Where is the derivative positive? All x. Where is the derivative negative? Nowhere, of course. And you see this function is always increasing. Here it's increasing fast, here it's increasing slow, but it's always increasing. So this function has no relative minimum or maximum. In fact, if you try to set the derivative equal to 0, you get some complex number. That means there's no real 0. That's really the point of that. Here's the second derivative. It's positive here and it's negative here. So, and it's equal to 0 at 6. So on this curve, 6 is an inflection point. Here the curve is concave down, and here becomes concave up. Yeah. Okay. Part 2, problem 2, is straightforward, just to calculate some derivatives and integrals. So here's a function, d of f is the derivative evaluated at x is equal to this. Now, if you just use the expression 2x to the 5th minus 107x plus 5, so this is now not a function, this is just an expression. Diff this is the command to differentiate an expression. Diff, the expression, comma x, whatever variable you're differentiating with respect to. And here, as we've seen before, is the command for the indefinite integral. And all these problems are the same. You know how to differentiate, you do it. You know how to integrate, you do it. This integral, you get something complicated, which simply means not every integral is possible to do, and this one can't be done. Here's the derivative and integral of tangent plus secant. And the derivative and integral, this is 2b. Sorry, this is 2c. Tangent plus secant. This is 2b. This is 2c. Let me just put in for completeness. Two D. So here we have the function x goes to 1 over 4 plus 49 times x squared. That's the derivative. And the integral of f of x with respect to x. If I write it with a capital I just get the statement of the problem. When I write it with a lowercase I get the answer, and this you should recognize is an arctangent, and here it is. If you want the definite integral, this is the definite integral of x cubed minus 1 to 1. You just put in limits on the x. It's exactly the same syntax. So all these problems are exactly the same. That's pretty easy. A, B. We do C. This is problem 3C. So we have this function, and this gave us the indefinite integral, but we want the definite integral. We want the integral from x going from 0 dot dot capital P I over 14. Yeah, so when this is evaluated numerically in the definite integral, this is what you get. Yep, that's what you get. Problem 4, we have a function log of x squared from 1/2 to 2. That's what the graph looks like. And when you integrate from 1/2 to 2, you get the area under the curve. That's what it is. So that's the plot. There's the graph. Just wanted to point out one thing. Here, when you compute the integral, you get an expression like this. And then if I convert it to decimal, I get this number. Here, it's almost the same integral, except instead of integrating from 1/2 to 2, I wrote 1/2 as 0.5 and 2 is 2.0. In general, in Maple, if your numbers are decimals, the answer will come out as a decimal. So I could have avoided this step if I knew I wanted a decimal answer and just written 2 as 2.0. All right, and the last problem, problem 5, we have the sine of x from 0 to 2 pi. This is what it looks like. If I draw it to scale, it looks like that. It's a little bit more interesting. And if you integrate just from 0 to pi, you get 2. If you integrate from pi to 2 pi, you get -2. If you integrate from 0 to 2 pi, you get 0. Why? Because, well, 2 minus 2 is 0, and also the interpretation of a definite integral as an area is it's a signed area. It's plus or minus. Area above the curve is positive, area below is negative. So this area and this area are the same in absolute value, but because this is negative and this is positive, they cancel out. That's the reason why you get 0. So 2 times this would be 4, but 2 and -2 is 0. Okay. And that is all of homework 6.